Hello, Mrs. Hassler here. We're going to be taking some notes on 2.5, evaluating limits analytically. Analytically is the same as saying algebraically. So we're going to look at limits today without using a table, without using a graph. I'm going to call this part 1 because I'm actually going to do 2 parts, one for this remote day and then one for your second remote day. Okay, so you guys should have watched the video on limit rules, and so as I go through this first example, I'm going to apply some of those limit rules. And so our directions are simply going to be to evaluate. And the first problem that we're going to evaluate is the limit as x approaches 3 of the rational function x minus 1 divided by x plus 4. And I call this a rational function because it is a function divided by another function. A rational number is a fraction, and so a rational function would be a function written as a fraction. And when you watch the video on limit properties, they said that if you have a limit of a quotient that is equivalent to the limit as x approaches 3 of x minus 1, notice I am going to put x minus 1 in parentheses because I'm applying the limit to both the x and the minus 1. So anytime you have a binomial or more, that expression should be in parentheses. Okay? And I'm applying the limit to each the numerator and denominator. X minus 1 is a line. So by nature, a line is continuous. I can directly substitute that 3 into my function. I'm going to get 2. And in the denominator, I have the limit as x approaches 3 of x plus 4. X plus 4 is a line, so by nature, it is continuous, which means I can directly substitute. And 3 plus 4 gives me 7. And so just by substituting 3 into my function, x minus 1 over x plus 4, I would get an answer of 2 sevenths. And graphically what that means is, let's see, if I would have a graph that looks something like this, okay, where I have a vertical asymptote at -4. Remember, a vertical asymptote occurs, so vertical asymptote occurs where the denominator equals 0, where x plus 4 equals 0, and x plus 4 equals 0 when x equals -4. Okay, so I would have a vertical asymptote at -4. And all this is saying is as x approaches 3 overall, as x approaches 3 overall, the y value I get close to on either side is 2 sevenths. Okay? So graphically speaking, I am continuous for that part of the function, and instead of having a graph, I could substitute 3 into my function and get the output. I wish they were all that easy, but they are not. So let's do another example. Number 2, the limit as x approaches 8 of x squared minus 64 divided by x minus 9. Now again, I have these limit properties, but I'm not going to take the time to write out these limit properties if we understand that applying a limit to a quotient means that I can apply the limit to the numerator and the denominator individually. Okay, and so that's what I'm going to do. I'm going to apply the limit by substituting 8 in for x in the numerator. Notice I'm not substituting anything in until my next step here, this step right here. And once I substitute my x value into my function, I've dropped the limit. Okay? Notice that I don't have any limit written here anymore. I can only drop the limit when I'm at the substitution phase. Okay? I'm also going to evaluate the limit by substituting 8 in for x in the denominator. I'm going to get 0 in the numerator, -1 in the denominator, and 0 divided by -1 is 0. So again, if I were to graph this function, and you could pause and graph it on your calculator if you want, but if I were to graph this function, I would see that as x approaches 8 on either side, the y value I get close to is 0. All right, let's take another look at a different function. So the limit as x approaches 5 of x squared minus 25 divided by x minus 5. And so again, I can apply the limit by substituting 5 into each numerator and denominator. Notice again, when I substitute that number in, I have dropped that limit notation. Once I evaluate by substituting, I don't need to write limit anymore. Limit is like my direction of, hey, substitute or evaluate as x approaches 5. I'm doing that, so I can drop the limit. Uh-oh, I get 0 over 0 here, and that sure is an interesting answer. In fact, this is the kind of answer that we say is indeterminate Okay, this is an indeterminate form. An indeterminate form could be of the form 0 divided by 0. If you ended up having something like infinity divided by infinity, infinity times 0, okay, infinity plus or minus infinity, I'm sorry, just infinity minus infinity, there we go, or 0 over 0. Those are all indeterminate. I really don't have enough information to make a statement about what the limit would be, and I have to do some manipulating, okay, in order to figure out what the actual limit is. If I were to graph this function, I would have a limit as x approached 5 on either side. Algebraically, it doesn't appear that way right now, but I can do a little manipulation to make this work. So you got to think back to your algebra skills. I'm going to go ahead and start at the beginning and rewrite my limit. But this time I'm going to manipulate my function by factoring that numerator. Remember, that is a difference of perfect squares. So x squared minus 25 factors into x minus 5 times x plus 5. Okay, and I still have this divided by x minus 5. So notice that I'm going back and I'm manipulating the function, which means I'm still going to write limit in front. I need to have that directive that I'm going to apply a limit. And the reason why I would manipulate, hopefully you can see it, is that I can divide a common expression in the numerator and denominator. X minus 5, that whole group, divided by itself, x minus 5, leaves me with 1. And 1 times x plus 5 is still just x plus 5. Now look, I'm going to go ahead and say that this is equal to, I'm not substituting in yet, okay? So if I'm not substituting 5 in for x, I still need limit written out front. And when you turn in your homework, that's one of the things I will be looking for. I have the function x plus 5 left over. And again, if I have a binomial or more, I should put parentheses to show I'm applying the limit to both terms. Okay, now I'm ready to substitute 5 in for x. So because I'm substituting that 5 into the function, I can drop the limit and I get 10. All right, so when you divide out a common factor, what is happening is that you have a whole value that makes the denominator 0. So we said before, up in problem, up at problem 1, I have a vertical asymptote where the denominator is 0. And that's because there was no common expression divided between the numerator and denominator. Okay, x plus 4 was not common to both the top and the bottom. But because I have a common expression in the top and the bottom, that expression that gets divided out means that there is a whole that exists at x equals 5. Okay, And so what actually happens is I have this function right here. I'll hold at x equals 5, and I continue on my way. And so the y value that I approach on either side is 10. And once I divide out that common factor, I can then algebraically determine what that limit is going to be. All right, just for fun, I have one more for us. So the limit as x approaches -1 of x squared plus 5x plus 4 divided by x cubed minus 2x squared minus 3x. Okay, and so again, I should always substitute. When I substitute -1 into this function, I'm going to get 0. When I substitute -1 into the denominator, I get 0. That answer is indeterminate. So I need to do some manipulation, which means I'm going to rewrite my limit. And I have polynomials, so I'm going to factor. So let's see, the numerator should factor into x plus 4 times x plus 1. Now what's interesting about the denominator is that I have an x term with each of these. And so I'm going to factor that x term out. That leaves me with x squared minus 2x minus 3. Okay? And now I can try to factor this even further. So the limit as x approaches -1 So now I can factor the denominator. I think that's going to be x minus 3 times x plus 1. Notice I still wrote limit as x approaches -1. I've not substituted in yet, so I can't drop that limit notation. Oh, and I do see common factors that divide out. That means I have a whole for this function at x equals -1. So what I'm really doing is I'm applying the limit to this function right here. So I'm going to go ahead from here and substitute -1 plus 4 divided by -1 times -1 minus 3. When I go, and again, I dropped the limit as x approaches -1 because I'm substituting into my remaining function in order to evaluate the limit. And so now when I evaluate, I get 3 over 4. So again, if I were to graph this as x approaches -1 from either side, the y value I approach would be 3/4. You just won't always have access to a graph, or you might not have a graphing calculator to graph. And so this is the way in which we evaluate limits analytically. Okay, you have a delta math to complete based off of this over rational functions. We'll take care of part 2 tomorrow.